Good afternoon, everyone. So I am going to talk to you today about the interplay between tectonic, erosion, and weathering, and climate. And I will focus more specifically on the potential impact of continental uplift on the long-term evolution of climate through chemical weathering and its impact on the carbon cycle. The potential role of uplift in climate evolution has been emphasized by the work of Ramo and Ruddiman over 30 years ago now. And these authors first linked the global cooling that is recorded during the Cenozoic period here to the uplift of the Tibetan plateau that followed the first initiation of India-Asia collision at around 50 million years ago. As you can see here, indeed, with the oxygen isotopic composition of benthic foraminifera that track the evolution, that reflects the evolution of deep ocean temperatures and also on the volume of the ice sheet on the poles, that our climate has been progressively cooling in the past 50 million years up to today. Of course, with some fluctuations interrupted by hyperthermal abrupt events, like at the Paleocene boundary, and by several more abrupt events of cooling, but on the cooling trend, nevertheless, over the last 50 million years. And a major event is also emphasized at the boundary between Eocene and Oligocene at about 35 million years ago, which marks the first permanent establishment of large ice sheets over Antarctica that are still present today, and that marks the entrance into an ice-house climate mode, that is our current climate mode, that is marked by lower CO2 levels and the presence of permanent ice over the poles at high latitudes. What Ramo and Ruddiman proposed is that this tectonic uplift of the Tibetan plateau could have enhanced, favored erosion and also reaction of silicate weathering over the continental surfaces that would have acted as a drawdown of atmospheric CO2 and led to a long-term overall climate cooling. Silicate weathering reactions can act indeed as, can consume atmospheric CO2, as Edouard has already presented in his talk. And these reactions can be summed up in this very simplified way, by which the carbonic acid that is generated by dissolution of CO2 in water, and if it is used in calcium-bearing silicates, that will release cation like calcium and also ion like hydrogenocarbonate ions that will be released in waters and transported to seawater, where they can precipitate as carbonate, releasing a part of the CO2, but also locking away another part of it, so that the net result of these processes from silicate weathering to carbonate precipitation result in a net consumption of atmospheric CO2. And this view had been initially supported by the timing of this initial collision between Asia and India, and also by this rise in the isotopic composition of strontium in seawater that has been at that time interpreted as an increasing contribution of strontium weathered from the continental crust to the budget of seawater. And this first view has been further supported a bit further by additional geochemical proxies that have been used as tracers of continental weathering rates at the global scale, like lithium, osmium isotopes, and that showed also concomitant evolution at that time with the signal of strontium. And it has been also supported by the long-term decrease observed in CO2, atmospheric CO2 data. However, this hypothesis has been challenged since then, based on several elements. Some authors have questioned the geochemical proxies that had been used to track the evolution of weathering rates through time, as these proxies can be influenced by additional factors than chemical weathering rates, like, for instance, the isotopic composition of the silicic crust weathered on the continent, or the weathering of specific lithologies like black shales, for instance, or also carbonates. In addition, we know for quite a long time that the lithology has a major importance on the efficiency of CO2 consumption by silicate weathering reaction. For instance, basalts, we know that it acts in a very more efficient way than the weathering of granite, but also different authors have emphasized the importance of additional chemical reactions occurring during chemical weathering of continental surfaces, in addition of silicate weathering. That is, for instance, the oxidation of rock organic carbon contained in the rocks, or also of sulfide minerals. Both reactions can act as a source, direct or indirect, of CO2. Other works have also showed that orogenese can favor an important CO2 sink through the erosion, transfer, and burial of organic matter, like, for instance, of contemporaneous vegetation, and a sink that, in the case of Himalaya, for instance, has been shown to be even more important than silicate weathering reactions. So this balance between all these different reactions that are involved in chemical weathering can push forward the effect of chemical weathering of the continent toward a sink or a source of CO2. And additionally, some authors have also emphasized the importance to consider the chemical weathering reaction that affect weathering products during transport of sediment from the erosion of the regolith to the food plains, where they can be further weathered, and their transport to the oceanic basins, where also reverse weathering reactions have been emphasized to act indirectly through their role in alkalinity as a source of CO2. And finally, another process that can be relevant when we look at the impact of orogenesis on climate is the relations that exist between weathering fluxes and denudation rates. It has been shown in modern environments that when denudation rates increases, it increases also the weathering of fluxes, because the weather erosion will remove the weathering products from the regolith and exposes renewed fresh rock to weathering. At low denudation rates, this will hamper weathering of rocks because of the accumulation of weathering products that can produce quite thick soil cover that will isolate the underlying rocks from the superficial fluids. And at the opposite end of this relation, at high denudation rates, erosion and weathering products can also be removed too fast from the regolith to be even further extensively weathered. So all these elements show that there is a complex interplay between tectonic, erosion, and weathering processes and climate. So finally, given all of that, what can be the impact of uplift in the carbon cycle and on the long-term climate evolution? So I'm afraid that today we still cannot actually answer these questions, despite all the progress that have been made in this topic. And our knowledge, actually, of the impact of origin of the carbon cycle very largely relies on the Himalayan Tibetan plateau uplift and with its very specific and peculiar lithologies, and also on the Cenozoic period that have focused a lot of work of researchers. And the Cenozoic period, which has entered about 35 million years ago on ice whose climate mode, is not the most common climate mode that exists through the history of the Earth, that is much more commonly marked by greenhouse, long-term greenhouse periods marked by higher CO2 levels and the absence of ice sheets at high latitudes. So in this context, the late Cretaceous period can provide an interesting opportunity to further study these tectonic, weathering, erosion, climate links. Actually, if we look back a little bit further in the past than the Cenozoic, up into the, and down into the Cretaceous, we can see here with the extension of the oxygen isotopic composition of benthic foraminifera that actually the beginning of this long-term cooling up to today began about 90 million years ago in the middle of the Cretaceous. So this late Cretaceous period here, from about 90 million years ago to about 65 million years ago, is marked by an overall greenhouse climate with no permanent ice at the pole. It is marked by a general climate cooling that is evidenced by several proxies in addition of the delta 18O of benthic foraminifera, like the text 86, for instance, or the delta 18O of planktonic foraminifera, that all show at all latitudes a marked cooling beginning in the Turonian and into the late Cretaceous up to the Maastrichtian. And this general climate cooling is associated with a concomitant decrease in atmospheric CO2 levels that hints to the implication of drivers in the carbon cycle. And it is concomitant, and it is what is interesting here, to a major uplift event that affects a large part of Africa. So this large uplift event has been evidenced by apatite fission track analysis that has been realized all along Africa, and it reveals this major episode within the 90-65 million years interval that is through the late Cretaceous, with different probably denudation rates that has been estimated from these different studies based on apatite fission track analysis, and that are up to 3 kilometers of denudation that have been estimated, with the most important part in the southern part of Africa and with more mild uplift in the northern part of Africa. And this is also supported by an increase in sedimentation rate during this period in the adjacent oceanic basins. So how did silicate weathering respond to this tectonic event? Could this event have enhanced silicate weathering intensity or rate and atmospheric consumption, and if it has, to which extent, and which part of the decrease in atmospheric CO2 levels could be explained by this process? So we have attempted in the last few years to answer these questions in the frame of an ANR project and also an ITN project. This has been done, of course, with a large team and collaboration of colleagues specialized like clay mineralogists, geochemists, tectonists, sedimentologists, and also modelers. And it has involved several PhD students and postdocs whom work you will see just afterwards. So the first step to answer these different questions is to bring constraints on the response of silicate weathering to the uplift of this African margin, and so it is to find a tracer that would allow us to track this response of silicate weathering, but at the local scale. As I said before, several isotopic systems have been used already to track continental weathering evolution, but their interpretation is hampered by the dependence to additional processes like the composition of the eroded crust of specific lithologies, and also the residence time in seawater of these elements is greater than the oceanic mixing time. It means that they provide a global signal which can be very useful to track global evolution of continental weathering, but they are unable to depict local response to tectonic and climatic forcing. And this is important because depending on which climatic belt, for instance, in which a tectonic uplift will occur, of course we can expect the impact and the response of silicate weathering and erosion processes to be different. So what we have done is attempting to apply for this distant path a new proxy of silicate weathering intensity that has been developed by Bayon and co-authors in modern environment, and that combines the isotopic composition of hafnium and neodymium isotopes in clays. The hafnium and neodymium isotope composition in samples is represented by the epsilon neodymium and hafnium here, that represents the deviation of the isotopic composition of the sample toward that of the chondritic uniform reservoir. The lutetium hafnium and samarium neodymium isotope systems behave similarly during magmatic processes, which results in a general correlation of the epsilon hafnium and epsilon neodymium values of most igneous rocks and sediments, which marks here the terrestrial array between mantellic radiogenic materials that yield positive epsilon neodymium and epsilon hafnium values, and old unradiogenic continental crusts that yield unradiogenic and negative epsilon neodymium and epsilon hafnium values. By contrast, these two systems are decoupled during Earth surface processes. A large part of this decoupling arises from mineral sorting during transport, that with the finest part of the sediments, the clays, a fraction of the sediments, yielding systematically higher epsilon hafnium values than the coarser fraction of the sediment. And within the clay fraction of the sediment, this fine fraction, if we can extract it, it has been shown by Bayon and co-author in modern environments that deviation of epsilon hafnium from this clay array that defines the correlation of hafnium and neodymium for the fine fraction of the sediment, this deviation here, that is represented by capital delta epsilon hafnium, is representative, depends on the intensity of chemical weathering during the formation of the clays. And the clays will then integrate this signal, transport it to the oceanic basin where they can be analyzed and give insights of what is going on the adjacent continent. This is linked to the more radiogenic hafnium composition of the most easily weathered minerals that will, when they are weathered, release this radiogenic hafnium that is then incorporating into the clays. And so basically, it means that the departure, the extent of the departure of the samples regarding its epsilon hafnium to the clay array, that is, if this departure increases, which is marked by an increase in this capital delta epsilon hafnium, this would reflect, according to Bayon et al., an increase in weathering intensity of the condition when the clays have been formed. So considering now the several isotopic records that we have acquired and that I will present to you, I am, however, wondering if we really track the weathering intensity, or it could be rather weathering rates, actually. So what we have done is target several ODP-DSDP sites along the African coast and also along the South American coast to have a comparison with the same climate belt here. So different ODP cores within different climatic belts and thus hydrolyzing conditions, and from regions affected by large in South Africa to more limited mild uplift in Northwest Africa. So I won't detail the protocol, but these marine sediments have been treated to extract only the clay fraction from the sediments that have been analyzed through mineral for XRD to reconstruct the nature of the clay minerals and the clay mineral assemblages, and also have underwent a sequential leaching procedure to extract only the signal of the clays and get rid of all the fractions that could record an oceanic signals like carbonate or ferromanganese oxide, for instance, before isotopic analysis. This method needs also to take some precaution. It can be impacted by the abundance of zircons because they are very rich in hafnium and potentially could dominate the evolution that we record of the isotopic composition of hafnium. So for every site that have been analyzed, we have checked, of course, the absence of correlation between epsilon hafnium and the concentration in zirconium, to ensure that it will not dominate and control the evolution of the signal. An important part when working on clay is that we want to analyze only the clays that are of detrital origin, meaning that are formed on the continent, and not the oceanic clays that can also form in marine environments. So this can be done by associating rare element concentrations, for instance, or also TEM observation that can give insights with the morphology of some clays, like here the smectite, and check that there is no significant clay orthogenesis on the seafloor, and that we track what is happening on the continent with this clay fraction. So to give you an example, before give you an overview of all the signals that have been acquired all along the African margin, here to present you first the Angola, what we have obtained on the Angola continental margin, which is located down the slope of Angola in a bathyal environment and in an area that is recording about 1 kilometer of denudation that is suggested by the people working with apatite fission tract data within the late Cretaceous. If we look first at the clay mineral assemblages, because they bear important indication also on the weathering processes, what we can see here is that the assemblages are largely dominated by smectite, but that there is a marked increase in primary clay minerals, that is chlorite and halite. Among the clay minerals, when a source rock is weathered, the first clay mineral to be produced when the physical erosion is more dominant and when chemical weathering is not very pronounced are halite and chlorite. And then when hydrolyzing conditions are more important in semi-humid, semi-arid climate with seasonal contrasted season, then smectite can be produced in soils. And if we move to more hydrolyzing condition, for instance in tropical environments, that's where we will produce kaolinite as clay assemblages. So these different assemblages in clay minerals can give us an indication on the dominant physical erosion versus dominant chemical weathering as well. And halite and chlorite typically are produced either in cold climates that limit hydrolysis, or in very tectonically active context with high denudation rates, which produce this kind of clay minerals. So if we look at this evolution, we can see that there is this increase in primary clay minerals during the middle of the late Cretaceous, relatively to the smectite. This can be summed up by the ratio between halite and smectite, which nicely here show here this increase in the proportion of this primary mineral, and thus that can be interpreted either as a cooler environment or also as an active, a more active tectonic settings. If we look in parallel to the evolution of the temperatures with the proxy existing, we can see that this increase here in highlight and spectate ratio occurs during this long-term cooling with a little offset, but here it is not very evident. So this cooling could have contributed to favor the production of highlight and not smectite, but this is occurring also during the climate of a tectonic pulse, and thus we have interpreted this increase in the proportion of primary clay mineral as enhanced erosion, likely linked to the tectonic pulse. This is also associated to a change in sediment sources that is marked by the evolution of neodymium isocomposition, and which is coherent with what we know about the structure of the margin, where progressively, with the denudation progressive, we will erode more ancient Archean basement that is marked by more negative epsilon neodymium values. And now, if I show you the big delta, the capital delta epsilon hafnium, that is a proxy of chemical weathering, what we see here is an increase of this big delta, which could be interpreted as an increase enhanced chemical weathering during the first increase in the proportion of primary clay minerals. So this means that here it is likely that this tectonic pulse would have enhanced chemical weathering at first, up probably to a plateau when the denudation could be occurring too fast to further weather the erosion product. So this is quite coherent with what we know from modern environments, when at high denudation rates we can reach a plateau and where a further increase in denudation rates could not further increase the weathering fluxes. So what we can see here is that increased denudation linked probably to the margin tectonic uplift could have favored weathering up to a plateau where denudation rates could be too high to further enhance weathering of minerals that could be removed too fast from the regolith. Temperature here is unlikely to drive this signal in weathering that we can see here, because a cooling event would tend to decrease the kinetics of weathering reaction and will favor rather a decrease in chemical weathering. So what we see here is probably a greater impact of the tectonic pulse in controlling the evolution of chemical weathering. Another interesting site to show here is linked to the uplift of the Southern Brazilian margin occurring during the late Cretaceous here, because this site is located in a relatively arid region during the Cretaceous. Again, if we look rapidly at the clay mineral assemblages, we see that the clay mineral assemblages are dominated by spectate, with higher proportion of highlight this time at the beginning of the late Cretaceous, and a decrease in the proportion of palygorskite, which is indicative of arid evaporative environments. So if we look at the whole signals acquired here and the capital delta epsilon hafnium, what we can see here is that at first there is a dominance of primary clay minerals during probably what is the climate of the beginning of the tectonic uplift, that is also marked by higher proportion of titan over aluminium, which sign probably a more pronounced physical erosion linked to the tectonic pulse. But this time, contrarily to the Angola margin, we don't see a response in the capital delta epsilon hafnium that marks the increase here of chemical weathering, but that follows this initial probably tectonic pulse. And here, an answer to this difference can be brought if we look at the evolution of palygorskite proportions that indicate here that arid conditions prevail with a lot of palygoscite in the clay mineral assemblages at the beginning of the late Cretaceous, but then decreases, indicating probably more humid conditions. So what we have interpreted the signal here is that probably the creation, the uplift, would have created a locally orographic climate with the development of more hydrolyzing condition on the side of the formed relief that is toward the ocean, and this would enhance chemical weathering, but not at first here, because condition would be too arid to allow a response of chemical weathering in these conditions. And we see this response after the initial pulse, once the conditions have been established and have been more humid. And so the last site to present you here is interesting because we have two sites on the southern part of Africa that are located closer and farther away from the continent, and it allows to compare the propagation of the signal and the difference and see if we have a difference between a signal acquired closer to the continent and more distantly to the continent. For the most proximal site here, what we see on this record is again an increase that is recorded in the capital delta epsilon hafnium, marking an increase in chemical weathering with a more or less stable data of epsilon neodymium, except here when we see probably an enhanced erosion of the Karoo basin that is present in South Africa here. And what is important here is that this increase in capital delta epsilon hafnium and in chemical weathering occurs a bit earlier than the two other signals that I have shown you, and it is beginning in the Cenomanian and preceding the long-term cooling that is recorded in the seawater temperatures. And if we compare with the most distal site here, that is an ODP site more distant than the continent, we can see that there is this increase again that is recorded here in black in capital delta epsilon hafnium, but there is an offset between the two signals. So this can be due to uncertainties in the age model because it is not very well constrained for this ODP site that is below the calcite compensation depth. But it can also show that the influence of different sediments and particularly clays that can be brought from a large by oceanic current from other area, and thus a different source of the sediment compared to the more proximal site. Anyway, if we look at the overview of all the sites that have been up to now analyzed, what we can see is that there is a systematic increase in this capital delta epsilon hafnium, which means enhanced weathering in all the sections of the margins that have been analyzed from the north to the south and along Africa as well as along South America. So what this indicates is that probably we have here at least a response of chemical weathering to an uplift that is affecting all the climate belts, even the most arid one, probably because we can have the establishment of an orographic climate and more humid conditions even in an arid belt to the side that is facing the ocean and created by the relief. That is a hypothesis, but it shows at least that there is some potential to work on this event because of this response that is common to all the sites. Now, if we put that in perspective with what I explained at the beginning of the presentation, of course, this is only just part of the story, because here what we track is the response of silicate weathering, and as I explained to you, there is also other additional chemical reactions that are important to consider to fully understand the impact of CO2 levels, of an orogen, and of chemical weathering of the continents. But in order to do that, what we need now to quantify really this impact and take into account the effect of lithology and the effect of this different reaction is, of course, to include modeling experiments. And this is the topic of Pierre Maff, who is in postdoc in the ANR in the last year. And he is actually currently doing this experiment. So I don't have yet an answer to provide about the impact of this uplift even to the atmospheric CO2 level. But just to say that the first experiment, at least, give an estimation of about almost 200 ppm of a decrease of atmospheric CO2 that could be linked to the specific uplift of the African continent, and which is about between 1/4 and 1/3 of the recorded atmospheric CO2 decrease during the late Cretaceous. So mainly what this new data bring is that there is this potential of capital delta epsilon HF to track variation in silicate chemical weathering, because as we have seen, it responds in all the margins that have been analyzed but to know. Of course, it doesn't work in every settings. We need exposure of basement because it will track the weathering of silicate material on the continent. And if all sedimentary formation are exposed in a large proportion, this is not a proxy that will be applicable. We have seen that in tectonically active context, enhanced denudation of the margin linked to the uplift could be and appears to be probably a major controlling factor of the response of weathering. And temperature variation, because we are in a cooling trend that would, on the contrary, hamper the kinetic of weathering reaction, appears to have a more minor impact regarding to tectonics. Even in quite arid climate, we have still a response of weathering, but that is delayed and appears when more hydrolyzing conditions can be established on the side of the relief that is facing the ocean. And finally, it shows at least that enhanced silicate weathering linked to this tectonic event may have played an important role in the climate cooling that is recorded to the late Cretaceous, but that remains to be quantified, and that will only be done through modeling. Thank you for your attention.